We're going to prove lemma 10. First, we can write gx as the product of small gx I from 1 to n. Here we have small g t equal to e to the minus t square over 2. So in here we only need to prove for small t. This means we only need to prove this lemma 10 for dimension 1. So some elementary calculation, we will have g prime t equal to minus t gt, and using the formulation for derivative of Fourier transform, we also have g hat prime t equal to minus t g hat t, and we also get g hat 0 equal to gt dt, and it's a Gaussian function, so it equal to 1 and equal to g0. We have here is a same BDE, same no ODE, the same solution of an ODE. So same initial value, so g mod equal to g hat, or the Fourier transform of Gaussian function, Gaussian distribution equal to g. So this is our proof of lemma 10. Now we go to the main theorem of this section. Is about it means the Fourier transform is continuous and a bijective mapping of a square space into itself. So now we have theorem 11 that say that the Fourier transform is a continuous and bijective mapping of the square space into itself. For u belong to s to the power of d, we have the inversion formula over here. We have an inversion formula over here. Here we define the f to the minus 1, f to the minus 1 at the Fourier inversion. We go f minus 1 as Fourier inversion. Fourier inversion. We can see it's over here. And follow this, we have a theorem 12. It states that there is a unique continuous operator f from L2 to L2 that extends the Fourier transform f to SRD and satisfy the equation the norm of u equal to the norm of fu for all u belong to L2. Furthermore, this operator f is bijective and it is inverse, as minus 1 is a continuous extension of f minus 1 onto SRD. This means this theorem states that we can extend our definition of Fourier transform on L2 to on SRD to L2. Now we're going to prove this theorem. To prove lemma 10, first we need to prove that HO belong to the Schwarz function, Schwarz space. Following the book, we have this inequality beta u has C to be equal to U1. From this we have U belongs to S, because this one is less than infinity. Because Fourier transform E linear. So we only need prove that is continuous at 0. Now we consider null sequence. Un in Schwarz space, or alpha beta un go to 0. Or this is equivalently to the derivative of un for all alpha beta go to 0 uniformly. So we have the right hand side of 1 10 to 0. In particular, we then C alpha beta U hat un go to 0. So un hat also a null sequence. So this is prove the continuity. To prove the inverse formula, we follow the proof of the book of Stein. Complex analysis of Stein. First, we define good kernel. Good kernel is a family of function. Then we do a preparation so that the f times the convolution of f and k x will converge uniformly. to fx, and from this we apply k equal to e2 minus gamma x square 1 over 2p, and apply the multiplication formula uv equal to uv, then we get the proof done. Now go to next slide. First we have the Plancherel formula. It said that the norm of Fourier transform of f equal to the norm of f and one more thing over here, we have the remark, that is we cannot define explicitly the Fourier transform of U belong to L square, so we need to extend from U belong to S, and this show that psi r of C will converge to U from Fourier transformation Fourier transform of U when r go to infinity. And in here, because we have about the space, we get integral over about the space, so it's well defined. We have this function well defined, so it's converted to U hat for r go to infinity.